Hello everyone, I'm Unji Park from KAIST. Thank you for joining to this presentation, and I will be presenting the study we've conducted, which is named Charlie and the Semi-Automated Factory, which is about data-driven operator behavior and performance modeling for human-machine collaborative systems. The semi-automated system is a collaborative system that requires active interaction between humans and machines. This kind of semi-automated system has been widely adopted across various industries, including the manufacturing sector. The semi-automated system remains automated status until a problem arises that the machine cannot solve on its own. So at this point, the machine requests human intervention to solve the problem to the human worker. In such scenarios, humans intervene in the process, relying on their background knowledge or their experience to make proper decisions. So these decisions can have a significant impact on work performance in addition to the machine operation or performance of the machine. So this interaction history between humans and machines is recorded as a vast amount of data in a computer called the human-machine interface. So leveraging this data, which is collected from machines, it is possible to quantitatively model the behavior, which is based on the operator's decision, or their performance resulting from that action or their behavior. However, despite the availability of multiple data streams collected from various many manufacturing machines, there has been room for utilizing machine-generated data for a fine-grained understanding of the relationship between behavior and performance of operators in the industrial domain. So in this study, we answered to these two questions. The first one is that how can the working behavior and work performance of operators be modeled using real-world machine-generated data? And the second one is that does the work performance vary depending on the work behavior tendency of the operator? So to answer these questions, we propose a large-scale data analysis methodology that includes data contextualization and performance modeling to gain insights into the relationship between operator behavior and performance. So as a case study, we collected machine-generated data from a highly automated tire building machine in a large tire manufacturing facility over a period of 6 months. So we collected 4 types of data from the machine. The first one is that trouble alarm data that records the history of trouble occurrence. And the second was that operator intervention data captured by the human-machine interface. And the third one is that product information data that contains information about the products, such as weight or a unique barcode of the tire in our case. And the production management data that contains process information. So we collected data, and at the first step, we integrated various types of the data based on timestamp of each data. However, we encountered a challenge in understanding the situation at that time. The problem was that it was difficult to understand exactly what problems occurred during the process and what actions the operator took to solve each problem. So to address this, we employed contextualization process to extract meaningful information from the dataset by incorporating relevant domain knowledge. The metadata used at this stage contains information about which part of the machine and which step of the manufacturing process is related to each event. So through contextualization, we classified temporal contexts such as shift, cycle, and event, and we also defined the machine state in detail. By matching trouble alarm events with corresponding HMI manipulation events, we were able to define the characteristics of operator actions. So for example, time, I mean the temporal context, was classified into the largest unit, the shift, which means the time an operator works once, and the shorter temporal context, the cycle, which means the time a single tire is produced. And the last one is the shortest event unit that contains alarm event or HMI manipulation event. In addition, the machine state is divided into normal, trouble, and pause states according to whether or not the machine is stopped and the cause of each stop. And also machine manipulation history and trouble alarm history were matched to see what action the worker took to solve which problem. So for example, in this figure, these arrows indicate manipulation events, and this X mark indicate the trouble alarm history. So through this figure, we could know that this green arrow indicates the solution to solve the problem X, which are related to the same part of the machine. So as a result, we presented a total of 3 types of factors to model the operator's behavior and performance. The first one is that operator-machine interaction factors. The second one is that environmental factors. The last one is that performance factors. These factors are devised by combining the context, each context, which are extracted by contextualization. So for the modeling, we use multi-level linear regression model, which is mainly used when data can be aggregated into higher level groups, such as operators in our case, and when there is heterogeneity between the groups. And we used performance factors as dependent variable, and interaction and environmental factor as dependent variables. And in our model, the random effect was operators, and the fixed effect was interaction and environmental factors. So as a result, the marginal R-square value, this value means that does not consider random effect, was 0.314 for the production rate, and the conditional R-square value, which considers random effects, was 0.5 for the production rate. And in more detail, looking at how significant each factor is to the result, the interaction factors that have a significant effect on production rate are the operator's reactiveness, proactiveness, and the amount of parameter modifications. And for a detailed explanation of each factor, please refer to our paper. And in the case of machine-related environmental factors, the number of spec changes and the number of alarm types had the most significant effect on the production rate. And among working environmental factors, such as weather and time of the day, the most important factor in production rate was the season. This is because the main material of tires is rubber, so the tires actually greatly affected by the temperature and humidity of the season. Through this study, we confirmed that performance can vary according to environmental context, such as seasons, as well as operator behavior, such as reactiveness or amount of parameter modification. And in our case, environmental factors have a greater influence on performance than interaction factors. In conclusion, we demonstrated the possibility of modeling operator behavior and performance by contextualizing real-world machine-generated data. We also revealed that work performance can be affected by the operator's work behavior tendency. And this is the last slide of my presentation, and thank you for your attention and your time.